All right, we're going to take a quick step back into chapter 13 for just a moment for 13.6. We're going to start talking about surfaces in 3 dimensions. So I wanted to start with this section because it's got some nice definitions and some helpful hints of how we can start thinking about how our surfaces are going to look. Again, I want to say at the front here, the upshot of this section is not that you are going to be able to draw perfect 3D graphs from this section. It's that you're going to just come up with some techniques so that you can help get an idea what this graph is going to look like before we go and maybe look at our 3D grapher. So we're going to start with cylinders and quadric surfaces. We're going to look at what the trace of a surface is, how we can get what the intercepts of a surface is, and how we can then use those traces and those intercepts to put together to get an idea of what our surface is going to look like. So first off, let's talk about a trace because we know what intercepts are, and intercepts are what you think they are. So that definition hasn't changed. A trace of a surface is a set of points at which the surface intersects a plane that is parallel to one of our coordinate planes. And so essentially what this means is that we are taking our shape, and we've got a picture of a shape right here. It's kind of a paraboloid shape. Which is a nice shape to kind of start with and think about. And the idea of a trace is that we're going to take and slice this shape parallel to one of our planes, either the XY plane, the YZ plane, or the XZ plane. So we're going to be parallel to a plane. So you can kind of think about it, it's always going to be kind of perpendicular or horizontal or vertical or horizontal, how we're going to be doing our slicing. And in particular, we're going to look at the traces that are on the coordinate planes. So the XY trace, the YZ trace, and the XZ trace. So that's what we have pictures of down here with this graph of our paraboloid. So the XY trace, that again, it's like we take a knife and we slice our graph right along that XY plane, just right parallel with it. And when we slice it and we kind of look at our two pieces that we end up with, they cut and they make this oval shape that we've got right there. And we could do a trace up here if we wanted. We could slice parallel to the XY plane and get another trace. It would just be, the same sort of shape, but a little bigger. Um, and then the YZ plane, again, that is slicing down here again, just along that YZ plane, which is the plane that's sort of back here. I'm going to take that off there. And when we slice that way, we get something that looks like a parabola. If we take our two pieces and just look at that end and look at that edge that we make, we get a parabola. Same shape that we get when we look at the XZ trace. We also get a parabola that way. And that's not true, with every graph that we get the same, looking trace from two of the sides. It happens a lot of the time, especially with these quadric surfaces. Um, but again, this is the idea of what happens when we slice. What shape does that make? What sort of two-dimensional graph do we get from that three-dimensional shape? So a quadric surface, I've been kind of saying this, essentially this is a quadratic in 3 dimensions. And so the general equation of a quadric surface is crazy looking. So notice we've got squared for each terms, we've got x times y, we've got x times z, we've got y times z, then we've got each term for each variable on its own, and then we've got a constant term j. And then this is equal to 0. And so A, B, C, all the way through J, those are all constants. And we need to make sure that at least one of A, B, C, D, E, or F are not 0. So that has to be the case for it to be a quadric surface. If it is 0, if those were all 0, that's kind of our note down here, that if all of those were 0, we'd end up with this guy, which is a plane, which is kind of the same thing, that we have in a definition for a quadratic function. In our quadratic function, we say that it looks like this. It's ax squared plus bx plus c equals 0. And we say that a can't be 0 because then if a is 0, then we just have a linear function. So same thing here. We need to make sure that we've got some sort of multiplication of variables. Now we're going to mostly see in this section, we're not going to, like I said, we're doing kind of a quick survey of this section. So we're going to keep it pretty straightforward, not going to get too fancy. Lost my z squared there. And we're going to mostly look at what happens if we have an x squared, a y squared, and a z squared, possibly some constant, and, maybe those coefficients, maybe they're positive, maybe they're negative, what's going to happen there. So let's take a look at some graphs. So like I said, I have two axes here because I want one to actually kind of draw the shape on. I'm going to do my best. I am not good at drawing in 3D as we've seen before. But I've got one where I'm going to draw our actual graph, or at least my best representation. And then another one where we're going to look at the traces and maybe the intercepts and think about those kinds of things. And actually, we could probably draw the intercepts on the proper graph. So let's start with the intercepts because that is something we know. And how we find intercepts is how you've always found intercepts. So when we talk about, the x-intercept, that's going to be when y is 0 and when z is 0. So if we make those two variables 0, all we're left with in our equation here is x squared over 25 equals 1. This we can solve for x, and we get x is equal to plus or minus 5. So we get two x-intercepts. And again, that should make sense in terms of what we know about an intercept, because an intercept is where we sit on that axis, and those points, that is going to be the point 500 or negative 500. And we can find our y-intercept exactly the same way, except that x and z are going to be 0. So we get y squared is equal to 9. So we get y is equal to plus or minus 3. So again, that gives us a couple of points here. So again, what's nice about this is while we're not going to get a huge number of points that are on this graphic, and we're just going to get a general sketch and kind of an idea of what this is doing, this gives us some actual sort of like grounding points to help us out and help figure out what the shape's going to look like. Something slightly interesting happens when we look at our z-intercept. So again, that's when x is 0 and y is 0, so we get negative z squared is equal to 1, or z squared is equal to negative 1, and that is not a real number. We likely know, it's very possible that that the solutions to this is plus and minus I, or plus or minus the square root of negative 1. That's not a real number, so that doesn't get graphed here in our real number coordinate system. So what this is telling us is that we have no z-intercept, and so our graph is never going to cross that z-axis. It's going to stay away from that z-axis, and that's going to help us a little bit here when we're looking at our traces. So now traces. So we're going to look at what's happening to this graph in the xy plane. So we're looking just at the xy plane, so that's going to mean that z is equal to 0. So if z is equal to 0, the graph that we're going to see when we make that slice of this graph, we're going to see this equation, x squared over 25 plus y squared over 9 equals 1. If it's been a little while since you've thought of anything about conic sections, or maybe you haven't, this is an ellipse. Hopefully I spelled that right. And something that I do to help myself remember what these graphs look like, and like I said, it's been a little while for me since I've done conic sections. So I will often go to Desmos and I will plug in what that graph is. So I have x squared over 25 plus y squared over 9 equals 1, and it's an ellipse. Ellipse is just a more general kind of circle. So it's an oval. And notice exactly on this graph where those intercepts are. It's exactly the intercepts that we just found. So what's nice about this is that that work we did with the intercepts and what we're seeing with the trace, that's making sense, and it's matching up. So our trace in the xy plane, it's an oval. So we can kind of draw an oval in there. So that would be our slice there. So again, what we're drawing is just actually that, red slice there. Okay, we're not trying to get the whole shape yet. We're just trying to figure out what's happening in that plane. So we can do the same thing for our other planes here. So the YZ plane, again, that's the one that's kind of flat back here. I'm going to erase that just to give us an idea of where that is. And that's when x is 0. So that's y over 2, or y squared minus, or y squared divided by 9. There we go, I can speak. Minus z squared equals 1. So I wasn't totally sure what this graph looked like. Again, it's been a long time since I've looked at these kinds of graphs. So I went into Desmos and I plugged it in, and it's a hyperbola. Now, something that we have to be careful with on this is that this is the y-axis right here, And notice it's crossing right there at 0, 3, and 0, -3. So again, the intercepts that we found. So, and our x-axis here is acting like our z-axis. So again, Desmos, I can't graph right here in 3 dimensions, and I don't want to get another axis there. So um, that x-axis is acting in place of the z-axis. Notice this graph does not cross that z-axis at all. So in terms of our traces here, what's happening is this graph is doing something kind of like that. It's got kind of these like quadratic-y shapes that are kind of coming off of the sides. Okay, and we've got one more. So maybe let's go with this color, and we've got the xz plane. So this is when our y value is equal to 0, and we get something very, very similar to what we got with the yz plane. Notice it's exactly the same. We've got that x squared over 25 minus z squared is equal to 1. This is also going to be a hyperbola. It's not going to cross the z-axis. And again, I did graph that trace on here, and here the y-axis is acting like our z-axis. And here's that trace, and again, notice it crosses the x-axis right at -5, 0, and 5, 0. So going back here, it's going to look like, look like that. Okay, so this is not too bad for my 3 dimensions here. And so what's going to happen is that it's going to keep kind of circling around these hyperbolas. And actually, I probably do this not too badly. So we maybe don't necessarily need to draw it on our other graph, and maybe instead of that, I'm going to wipe this one and just draw a little picture of what I think that shape actually does look like. And it looks kind of like, if we looked at it more upright, it's going to look something like this. We got hyperbolas kind of on the sides, and that's hollow in the middle. So it's kind of like a cylinder that flares out at the top and flares out at the bottom. And then what I did is I went ahead and I graphed this in our 3D grapher. So there's a link to this in Canvas. I'll show you guys in class, but if you can find it in the Start Here module in the technology, and you should also probably see the link when I move to it. But what we need to do if we're going to graph this on that grapher is we do need to solve it for one of our variables. It really doesn't matter which one. I tend to solve it for z, just because that's what I'm used to, and that'll make sense probably as we move on in sections. But I do generally solve this for z, and so we get plus or minus the square root of x squared over 25 plus y squared over 9 minus 1. And we've got to remember that plus or minus. If you don't graph it with the plus or minus, if you just do the plus, you're just going to get the top half of that shape. You're going to get it basically from that original trace here in the xy plane. You'll just get sort of this part of the graph. So I did go to the grapher and graph it. Whoa, it's already spinning. There we go. So that's what it looks like. Kind of looks like that. And again, I didn't draw the most perfect graph when I was looking at it, and drawing my general shape on our notes, but that's okay. But I got an idea of kind of what it looked like, that it's got that hollow center. And again, when we look at it sort of straight down the z-axis, which is what we're doing, there's the z-axis. We look straight down that z-axis. See, it's marking that point. Let me see if I can get it to not mark that point. Maybe not. Maybe I can't. No, that's all right. It's just marking a random point on there. Sorry about that. No, it's still just going to show it. That's all right. But we can see that oval. And also if we look at it sort of straight on the x-axis, you can see that hyperbola that goes through -3 and +3 on the y-axis. And if we look at it this way, you can see that hyperbola that goes through 5 and -5 on the x-axis. All right, now it's going to keep spinning. All right, let's take a quick look at another one. Again, I have 2 axes on here, but we may not need that second one, depending on how well I can draw things. But if we find all of the kind of same things that we wanted to find before, those intercepts, because again, that kind of helps us give an idea. And what that also helps me do is, when I'm back there looking at that graph, that helped me make this scale that I have over on the side where I was formatting the axes. You get that from this little button right here. Oops. You should mess around with this program. It's really kind of cool. The add to the graph, that's the kind of curves that you're going to add. I had to add a function f is or z is equal to f of x, y. So that's why I had to make sure that it was in terms of x and y. But notice if you go a little further down, you also have x in terms of y and z and y in terms of x and z. So you have options with how you do that, but generally we solve it for z. And I had to add two of these. I've got the positive square root and the negative square root. But knowing where those intercepts were made me realize I needed to extend my x-axis, extend my y-axis. Because when you first go into graph this, it starts with like -2 to 2 on all the axes, and I wasn't seeing anything. And I was sort of sitting there wondering why I wasn't seeing anything. Well, I didn't have uh, my window big enough. So for that x-intercept, again, back to this one, we plug in 0 for x and y, and we get x squared is equal to 0, which means that x is equal to 0. So we got the point 0, 0, 0, which is going to sit right there at the origin. And that means that that is actually our x, y, and z-intercept. We can double check that we aren't going to get anything different when we try to find any of the other intercepts, because there could be multiples, but no, that's what we're going to get. We're going to get 0. So 0, 0, 0, that is the only intercept that we have. And then if we look at our traces, so again, we want to look at what's happening when we slice that graph on the xy plane. Oops, I want to put my dash a little too soon, that xy plane. So we get y, or 4y squared is equal to x squared. So if you're not sure what this looks like, we can solve for y squared, or solve for y. And we get y is equal to plus or minus the square root of 4x squared. So we get y is equal to plus or minus 2x. That's two lines. That is linear. So our trace is literally going to be these two lines, which is kind of interesting. If we look at the YZ plane, okay, let's take a look what happens there. We get x being 0. Ooh, something interesting happens. Ooh, this is only true, this equation is only true when everything is 0. That's the only time that equation is true, because you're squaring both of your values for x and y. So the only thing you get when you slice on the YZ axis is that point, our intercept that we found, which is really kind of interesting. It'll make a little more sense when we get the rest of this here. When we slice on that xz plane, we're going to get z squared is equal to x squared, or that z is equal to plus or minus x. That's another line. So that's going to go kind of out this way and back down that way. And that's going to go out this way and back down that way. So when we slice, we're getting lines like that. And what's actually happening with this is that we are actually going to get cones when we go out both ways. The cones will be the same. There we go. We're going to get two cones, and they're going to meet up right there at 0, 0, 0. And again, you know, part of the reason why I know that that looks like cones when we've got lines like that is because I graphed some of these. So it's totally okay to draw those traces and think about maybe, okay, what's happening with this? Um, but then also going to that 3D grapher and saying, okay, what is that going to look like? So again, to get this picture, I had to solve that equation that we had for one of our variables. Again, I generally choose z. There's, you know, no necessarily good reason for it other than it's just the convention that we have. Sometimes when we've got other types of functions, it will be easier to solve for one of our variables versus another. So that may help make our choice. But for right now, oops, that moved too much. But for right now, solving for z is just as easy as solving for any of our other points. So we might as well. We just have to remember if we've got z squared, we've got to do that plus or minus. Otherwise, you're only going to get one side of things. So again, back to that graph, we've got our two cones. And again, we can take a look at the traces if we look straight down on the y-axis. we see the XZ trace where it looks like two lines. If we look straight down on the Z-axis, again, looks like two lines when we slice that. And if we looked right down on the X-axis, it's going straight into that cone, and it's that single point. You can kind of see it here even a little bit better, that it's going to be that single point. So it's perfect, two perfect little cones stacked end to end.